morning, everyone. Welcome to the first session of the second day of the COS meeting. My name is Son. I'm from Seoul National University. I'm very happy. It is my great pleasure to chair this session. This session is invited talk by Professor Ivana Damjanov, who's a Canada Research Chair Professor at St. Mary's University. She's also a brain pool scientist who's invited by the Korean National Research Foundation. So she is going to stay at the SNU for the next 6 months. So if you want to talk to her or if you want to collaborate with her, please contact her directly and we can set up the meeting with her. So today she will give us, she will talk about the structure and spectroscopic evolution of Quiesent galaxies in the middle-aged universe. Please welcome Professor Damjanov.
Thank you very much, and thank you, Juby, for that introduction. So before I start, I should acknowledge all the people that contributed to this work. We are a small but vibrant group. So first of all, Juby-san, who is actually the manager of the large fraction of the data set that I will be showing, actually most of it, and who provided a lot of data products and of course a lot of interpretation of those data products that went into this work as well. Then Margaret Geller, she is from Harvard-Smithsonian, and she's basically the mastermind behind the spectroscopic survey that I will introduce and use throughout this talk. Yosuke Utsumi from Stanford, he's the key player in developing of the Hyper Supreme cam on Subaru that we have also been using. And Jan Del Antonio from Brown University, who is expert on reclancing and who provided valuable advice and insight into measurements of galaxy structural properties, including sizes and shapes. All right, so let me start with this overview picture of how a massive galaxy that is nowadays quiescent and big develops. So we think, based on various studies at various redshifts, that it starts very early on, and James Webb telescope is pushing that to very, very, very early ages of the universe. And it starts as, at the beginning, it's a dusty starburst galaxy, vigorously forming stars over here, formed through probably a very wet and very major merger of two similar galaxies. Then it goes through the quasar phase over here, the so-called compaction. So after that, it becomes a quiescent compact galaxy that is then evolving passively through most likely a series of mergers with smaller objects to become what we see today. So what we are looking at, our small group, is the evolution of galaxies between this phase and this phase over here. So redshift that we cover is below redshift of 0.6. So it's around 5 to 6 billion years of cosmic size, which is quite a big fraction of cosmic history. And the aspect of the size of the evolution of galaxies that I will describe here is the evolution in size, or the evolution in structure of light profiles of galaxies. So what you can see here is the relationship that I will refer to throughout the talk, and that's a relationship between the size that you see here, and the proxy for size here is so-called half-light radius. Half-light radius comes from 2D modeling of the galaxy light profiles, and if you like equations, here is what the model looks like. That's a Cirsic profile, and here is the parameter RE that is over here, and it basically ensures that half of the total mass of the galaxy is within it, okay? Or total light, I would say, because it's based on the light profiles. And here is, of course, stellar mass from SCD fitting. And then these small pictures that you see here are pictures of real galaxies from Hubble Space Telescope. And the ones with crosses are quiescent, they're not forming stars anymore. And the fluffy ones are star forming. And they are observed at redshift of around 2-ish. And there are several things that you can see, I hope, in this figure. So first of all, these crosses, so quiescent galaxies, are several times smaller than their fluffy counterparts at the same stellar mass, so smaller than star-forming galaxies. And second of all, they're also several times smaller than the relationship between size and stellar mass that we see at redshift 0, which is here in white, represented by a white line. So the question is, if these galaxies already stopped forming stars, how do they become this large, right, over the few billion years of cosmic time? And there are many options to consider, and people have been considering them for years. And here are the most likely ones. So first of all, because they're already quiescent, the idea is that they should probably evolve by actually merging with other systems. And in terms of mergers, there are several options again. One of them are, sorry about that, are major mergers. And the result of a major merger is shown here with a red arrow. So basically, the amount of size growth is proportional to the amount of mass growth in a major merger. Major merger is when two galaxies are of similar size. The problem with that is that this will move galaxy along already established size stellar mass relation and not perpendicular to it, which we want. So the other option is to invoke minor mergers, series of them. And in this case, that's the other red arrow over here. The increase in size is much more efficient with respect to the increase in stellar mass, and it moves galaxy in the right direction. Okay, so that became the preferred channel of the growth of quiescent objects. However, when we think about the population, we can ask ourselves, but is that the whole picture? Are there any other effects that are significant, right? And here is one that might be and may not be as obvious. And that's because it does not affect individual galaxies that I showed before, but it does affect the population as a whole. So here you see size mass, oops, sorry about that. I knew this would happen. Here again, I show a size mass relation. I warned you, it will be in every other slide, basically. This is also from HST. This is 3D HST, and you see blue and red points, so star-forming and quiescent galaxies observed from redshift of around 0, basically, to redshift of 3. And the point here is that blue points, so star-forming galaxies, are always larger than quiescent galaxies in red on the left-hand side. And on the right-hand side, you see that star-forming galaxies grow as well as the quiescent ones. So if you put these two pieces of information together, then you can think about the effect that the addition of these star-forming galaxies that will eventually become quiescent to the quiescent population as the universe age should change the average age of the quiescent population as well. So that's additional effect, and it's quite big because the difference between sizes of two populations is quite big. So the question is, how big is this effect, and does it maybe dominate at certain redshifts? Okay. And just before I get into answering that question, if you're asking yourself, so how far does it go, this size evolution? Well, the very new results from James Webb Telescope tell us that it actually goes on even beyond redshift 3. So these are the results for redshift between, you can see it here, in the color scheme between 3 and 4, and the galaxies at those redshifts are in circles, and you can see that the relationship they establish in the size mass parameter space, so that's in red, is actually smaller below the relationship that we see at slightly higher redshift that I showed in the previous slide, and that's in solid black. Okay, so it goes on. This evolution goes on for 10 billion years, and so it's important to understand what drives it, right? All right. So, in order to disentangle these effects of these different processes that can, influence either individual galaxies or the population, what we need is to segregate galaxies by their average stellar population age, and then to follow these subpopulations as they age. So for that, we need large, dense spectroscopic surveys that cover redshift interval that is broad enough to capture the growth of various subsets, and spectra that are covering wavelength range that captures this so-called D4000 or DN4000 index that is a proxy for galaxy age, cell population age. And just to remind you why that is, here is one example of one of the spectra that we use, and this is the inset into the regime around 4,000 angstroms, and D4000 is the ratio of the median or the mean flux just after and just before 4,000 angstrom break. And as you can see here, as the galaxy ages, this D4000 goes up, the ratio between blue and red goes up, because the red part, which is just below 4,000 angstroms, goes down, the continuum goes down due to a series of absorption lines, so-called metal blanketing in the atmosphere of low mass cool stars that dominate spectra of galaxies at these higher ages. Okay, so that's what we will be using. And the sample that allows us to do that is HectoMap. So I think many of you have heard about HectoMap already and seen this cone diagram that Juby produced, which is just amazing. And just to give you a bit of overview what it is, it's a 52 square degree redshift survey done with HectoSpec on MMT in Arizona. The targets for the survey were selected to be red, and there is a magnitude limit to the survey of 21.3 in R, and we have collected 100,000 galaxies. So each point in this cone diagram is a galaxy. We are sitting here on the left-hand side at redshift 0, and basically the survey is mapping the cosmic web from redshift 0 all the way to redshift 0.6. So this is the kind of data set that is necessary in order to perform the analysis that I will describe next. All right, but in addition to the redshift survey that will give us precise distances to galaxies, and of course characterize their stellar population, well, we also need images, because we are going to look how galaxies move in the size mass parameter space. And for that, we use images that are actually available for this patch of the sky, and through the HSC SSP, so Hyper Supreme PAM Subaru Strategic Program survey. And you can see the position of HectoMap on the globe here. So it's on the Northern Hemisphere. And what we use is I-band, at least for now, I-band images to get the sizes that I will show you next. And just before I do that, here is a small inset. Oh, sorry, this is 2 × 1 arc minute inset of the coverage of HectoMap by HSC. This is a 3-color image. I think it's GRI. And it's just to show you that these images capture both very small details of individual galaxy profiles, but also over a very large, in our case, 52 square degree of area, contiguous area. So that is the amazing, those are the amazing properties of the data set that we're using. So this is the size mass relation in 4 mass bins, 4 redshift bins. And there are 2 surveys here. So on the left-hand side, you see HectorMap. And on the right-hand side, oh, sorry, it didn't actually show up well. So there are color points on the right-hand side maps as well. And the point here was that this dense survey, HectorMap, which is 10 times larger than the survey I'm showing on the right-hand side, which is also a CFA redshift survey led by Margaret Geller, it's shells, that the fact that it's 10 times larger, an order of magnitude larger, gives us the opportunity to actually map this difference between size and mass of galaxies with different stellar population ages much better. So here you would have seen that the circles are sparsely populating the parameter space, giving the hint of what here is quite obvious. And here you see obviously what is happening. So each point here is a bin of mass and D4000 measurement. And then the size is the average size for that bin. So what you see is that all red points are always below blue points. What does it mean? Large D4000, old galaxies are always smaller than the young ones. And that goes on from redshift 6 to redshift 0.2. Unfortunately, in redshift 6, this is not that clear because we don't have dynamic range there. As I said, this is a magnitude limited survey, which means that mass limit of the survey is changing with redshift. So we only have highest mass galaxies at the highest redshift bin. The separation is not that clear. But as you see, inclusion of smaller and lower mass galaxies at lower redshift, you can see this separation better and better. You can see fan open, right? And just to emphasize, there was no smoothing other than, making bins of mass. There was no smoothing of color in this plot. So this is the comparison between 52 square degree survey and 4 square degree survey with similar properties otherwise. So then spectroscopic survey, very high quality imaging coming both from the HSC in both cases. So here in 4 degree survey, you see the hint of this separation by color, right? But here it's quite obvious. So that's the point there. All right, so now let's move and look at the properties of this survey on the left-hand side a bit better. So in this case, I'm showing again size-mass, stellar mass relation, but for 2 very narrow redshift bins that are separated by 1 giga-year, 1 billion years of cosmic time. And what you should focus on are the histograms. So on the upper 2 histograms show the distribution of masses in 2 bins, and you can see from the distribution itself that it is the masses are the same, and that's by design because we limit the mass to be the same for two bins. But on the other hand, the distribution of sizes, which is on the right-hand side, is quite different. So in other words, you see in orange this tail towards smaller sizes that are present in higher redshift bin, which is called orange, and not in the lower redshift bin. And the other thing that I should point out here is that these are only galaxies that are coming onto the sequence. So they have D4000 between 1.5 and 1.6. So that's the lowest D4000 in our sample. Okay. All right, so now let me explain how I will use this D4000 to follow all these subpopulations that I introduced over the interval of the survey. So this is the plot that shows how D4000 grows with look-back time or cosmic time. And this is based, of course, on models. So these are the synthetic models that we're using. It's FSPS. And of course, we have some assumptions about star formation history, about methodicity, and then we follow these models in time and measure D4000 for every synthetic spectrum that we have. And what this plot shows that depending on what D4000 of a galaxy is when it enters our survey, and it enters our survey here, here on the right-hand side element, that will determine what its D4000 is at redshift 0. So if it enters our quiescent population here, right, it reaches D4000 at 1.5 at redshift of 0.6. At redshift 0, it will have D4000 of almost 2, and so on. If it has higher D4000, this is teal here, then it will have at redshift 0.6, it will have higher D4000 at redshift 0 as well, and so on and so on. So by separating these subsets of spectra with different D4000s as they enter our survey at redshift 0.6, we can actually follow their descendants by selecting larger and larger D4000 spectra at lower and lower redshift. So the bins of D4000 that we use at different redshifts are here in these shaded boxes, and that is what we do. So let me show you how it looks like. Here is the example for the objects that are here in this plot, in this bin over here. That's where they start from, and then we follow them by looking at all these other bins that cover the red line. So we start at redshift 0.6. This is their size-mass relation, and then we will do redshift 0.2, which is the lowest redshift in our sample. And you can see how things change. I will give you the summary plot as well. This is just to illustrate what we are doing and how things move in this complicated three-dimensional parameter space. This is another example. This is for the galaxies that are already very old in terms of their stellar population age when they enter our survey at redshift 0.6. So that's why they are all yellow already at redshift 0.6, and then they age to redshift 0.2. Again, you can see how things change. Here is the summary plot. It's very busy, so I don't expect you to get much out of it, except an overview of all of these different subpopulations that you can see. So we have 5 different subpopulations that are defined by D4000 at redshift 0.6. You see that over here. It's from top to bottom. We show in each panel stellar mass and of course size, and then from left to right, the redshift decreases from 0.6 to 0.2. All right. So to summarize what is actually happening in this busy plot, I will show you now how the parameters of this size-mass relation that is given here by these lines are actually changing with redshift. Okay? So the parameters of that size-mass relation are slope and 0 point, of course, it's a line. So it's a gradient of size with stellar mass and the characteristic size you see how galaxies are populating this parameter space. This is highest redshift bin. And you can see how they enter it from this little clock over here. And the two distributions correspond to these newcomers, so very young quiescent galaxies that are entering the population, and red, which are galaxies that are aging already over this redshift bin. So they're at higher default counts than this redshift bin. And so here I'm just going to populate this slope versus redshift and 0 point versus redshift parameter space with different points as we go in redshift. Okay, so this is 0.5 to 0.6, then this is 0.4 to 0.5, how many points? This is 0.3 to 0.4, and finally this is 0.2 to 0.3. So now we have on the right-hand side at least a summary of how the slope and the 0 point of the size stellar mass relation evolve for three populations. Two of them are subpopulations, so that's red and blue that correspond to these distributions that you see on the left, so young and old, let's say, galaxies in the sample, or newcomers and aging ones. And then the white lines correspond to the overall quiescent population, the sample. So let's focus on the evolution in 0 point, or the characteristic size. So you can see that the increase in size of the aging population, which is in red, is slower than the increase in size of the newcomers, which is in blue, and then the increase in size of the total population is in between. So clearly, the fact that the size of newcomers is larger and that it increases is contributing to the total increase in size that we see. Now the question is, what is that increase? How much does it increase? And it turns out that the increase, the contribution to the overall population is not very strong. And I will explain this in this final figure related to the size evolution. And in this figure, again, you see how 0 point goes with redshift. These different circles correspond to different quiescent aging galaxies in our survey. And then the squares are these newcomers. The shaded area, the gray area, corresponds to the predictions based on very simple models of a series of minor mergers, plus some estimates for the minor merger rates from observations. So you can see that the newcomers, these newly quenched galaxies, are shooting over the predictions, the range of predictions from models, while everything else is within that range. However, what is also within that range are white circles, which is the total, the full quiescent population, which tells you that although newcomers are not following the predictions of minor mergers, why would they? They are not, the size evolution is not strong enough or not contributing enough to change the explanation for the evolution for the total population. Okay? And the reason for that is that there are not that many of them. So only 15% of our galaxies are newcomers. And to quantify all these, the imprint of all of these different subpopulations, I can tell you that overall, quiescent population changes its average size by 50% over this redshift interval. 37% comes from the aging population, and the rest are newcomers, so only 11%. So yes, there is an effect, but it's not major. So mostly what dominates the size evolution is the evolution of the aging population, which seems to be driven by series of minor mergers. Okay? All right. So the other thing that we can explore here is dynamical mass, because in addition to measuring sizes, we also have velocity dispersions that are coming from full spectrum fitting of each kind of where main difference is that both Sloan and our sample are mass limited, while the high redshift samples are really incomplete. Okay, so let's see how that comes into play. So here you see the distributions of various parameters in all these samples going from redshift to velocity dispersion. So redshifts are of course different, that's by design, but what is also different are other parameters, distribution of other parameters. So histograms in red, blue, and gray are different both for stellar mass, for all three, stellar mass, size, and velocity dispersion. And is that a problem? Well, let's see. If we make all these samples similar in size, or at least not to go below the size of the lowest mass galaxy in the high redshift sample, this is how the distribution of size and velocity dispersion is going to look like. So compare these two panels with these two panels. So sizes are still different, right? So the higher redshift sample is going to have sizes that are much smaller than the lower redshift sample, and this tail of large galaxies is going to be larger and larger, more and more populated at lower and lower redshift as cosmic time goes by. On the other hand, velocity dispersions are becoming much more similar between samples, which is a key here. So let's see how these different parameters that go into dynamical mass actually evolve. So this is the evolution of size. You see size normalized by its value at redshift 0. So this is the characteristic size that I was talking about. And as a function of loopback time, or redshift if you wish, these different contours correspond to Sloan in red and Hectomap in blue. High redshift samples are given by individual points over there in gray, and then heavy circles are medians of different redshifts. And then you see the fit as well. There are two fits depending on whether we fit only the mass limited sample or not. It doesn't really matter. What we see is that size evolves with redshift with the exponent as a power law with the exponent of around minus 1.5. And that's not that new. That is something that has been already suggested by other surveys over the years, and miraculously, this exponent is always around minus 1.5, or in most cases, 9% of cases is minus 1.5. So this is a very strong effect that is very easy to detect once you have the right samples. Now, if we go to velocity dispersion, so this is the equivalent plot, but for velocity dispersion, it's normalized by its value at redshift 0. This is lookback time. What we see is something quite different, right? There's no evolution. And the reason why there is no evolution is coming from the histograms that you already saw. All the distributions become very similar once you make sure that you're covering the same stellar mass range. Okay? This is actually quite different with respect to what's been reported a few years ago, let's say, where they see the upward evolution, so positive evolution with redshift in velocity dispersion, and you can see why that is. So in previous studies, what was done is that this intermediate redshift range here was completely omitted. So what I did was combining this point with these 2 points, or similar, getting the upward evolution. Okay? So when you do it more carefully, I would say the evolution basically goes away. All right, so let's now combine all this together and see how dynamical mass changes. So here I'm showing actually two plots, two panels. One is dynamical mass versus stellar mass here, and you have all these different samples given in different contours. Again, red is Sloan, blue is Hectomap, and then high redshift samples color coded by redshift are by individual galaxies.
And the lines correspond to the relation between stellar mass and dynamical mass for hectomap here in black and for Sloan here in red. And here you see what the difference is. First of all, the slope of the relation is 1, good. And second of all, there is an offset. And that offset changes between redshift of 0.4, which is sort of like average redshift of our survey, and redshift 0. Right? And it changes by a factor of 2. So you can see that from these two numbers. And here is the evolution in dynamical mass, and you can see again it's a power law. We model it as a power law, and here the exponent is around -2. Okay. So what is the explanation for that? Well, there is a very simple actually explanation for this, and that is that because we now know that velocity dispersion does not change, size changes, you combine them together, and then it means that with time, as the galaxies grow in size by adding fluff to their outskirts, their effective radius changes and is probing larger and larger fraction of dark matter. And that is important because part of this, let me just go back quickly, of this factor over here, K is, or what goes into this K factor is also the fraction of dark matter within effective radius. Okay.
So that is a very simple explanation of what is going on in observations. And I think that is everything I wanted to say, for now. And I will just finish here with, now this is not working, okay. With this movie, maybe this is also familiar. This is a movie that Juby made, and that's another timeline, another time scale. And this is how hectomap was assembled. It takes 15 years to get 100,000 spectra, and it gives you this beautiful data set that can be used to probe, among other things, the evolution of quiescent populations in various aspects. And many other surveys that are coming online from PFS to MSC, 4 moons, and foremost moons and others, will actually extend that to even higher redshifts. We will be able to probe all these evolutionary trends to much better precision and accuracy over time. So thank you very much.
Thank you very much for completing the talk despite the technical problem. Because we are running out of time, we'll take 1 or 2 questions.
So thanks for a very nice talk. First part of your results, you measure the size based on the light distributions, like half-life radius. So if you could have measured half mass size, then you show the summary plot, the size is moving up and down. How much would you expect the evolution?
Yeah. Well, you're reading my mind because that's exactly what we plan to do next. Because we do have, as I said, we do have images of these galaxies in multiple bands, so we can actually do spatially resolved SCD fitting. So that's what we will do. But the indication from higher redshift, where this has been done already, because there we have HST space-based observations, suggests that the difference between the size in light and size in mass is larger at higher redshift and becomes almost negligible, 10% or something like that, at redshift below 1. So this will not, I think, change much, but we will do that. That's exactly what we're doing next. Yeah.
Thank you.
Professor Myung-Shin 회원님.
This may be a minor question, but so you divided sample into like different DN4000 and did analysis, right? But along the way, from redshift 0.6 to 0, when they can evolve and there should be some minor mergers, that could mix the stellar population with something other. So, are you worried about it? I mean, that could change the DNA 4000 evolution, how it evolves, from the
Right.
mission.
Right. It could, depending on what kind of mergers are happening. So here, the idea is that if the mergers are minor, that means that all that material and possible, minor star-forming effects are happening in the outskirts. And what we are capturing with D4000 is the central part, because it's a fiber-based spectrograph that we are using. We're capturing the central part of the galaxy that is not changed by this addition of chemical.
Thank you. And let's thank our speaker again.